Most Snowflake interviews start right here with the core architecture. Architecture questions can make or break your Snowflake interview. In this episode, I'll throw at you some of the critical ones that reveal whether you truly get how Snowflake runs, not just what it does. Alright, let's kick off episode 1. We'll start with the questions on the core architecture. From an engineering standpoint, what makes Snowflake's architecture different from traditional data warehouse? Snowflake is fundamentally different because of its shared nothing architecture, meaning each compute cluster runs independently with its own CPU, memory, and cache without sharing resources with others. Additionally, traditional data warehouses tightly couple compute and storage. So when you try to scale one, you end up scaling both, which often leads to bottlenecks and even downtime. In Snowflake, compute and storage are completely decoupled. Your data sits centrally in compressed micropartitions on cloud storage, and compute happens through independent virtual warehouses. Each can scale up or out without affecting the others. That's what gives Snowflake true concurrency and elasticity. Multiple teams can run heavy workloads at the same time without stepping on each other's resources. It's also cloud native and service oriented, which means all the heavy lifting, metadata management, query optimization, and access control is handled automatically. So while traditional warehouses scale vertically by adding more power to a single machine for higher performance, Snowflake scales horizontally by adding more compute clusters to handle bigger workloads in parallel. Walk me through how Snowflake's layers talk to each other when a query runs. Sure. When a query runs in Snowflake, three main layers come into play: storage, compute, and cloud services. And they work together like a coordinated system. It starts with the cloud services layer, which is basically Snowflake's brain. This layer handles authentication, query parsing, optimization, and metadata management. When I submit a query, the cloud services layer figures out what needs to be done, builds the execution plan, and then passes the job to the compute layer for execution. The compute layer, made up of one or more virtual warehouses, is where the actual processing happens. These independent compute clusters execute the query by scanning micropartitions, performing joins, aggregations, or any transformations needed. During this process, the compute layer pulls the required data from the storage layer, where Snowflake keeps everything in compressed, immutable micropartitions stored on cloud object storage like S3, Azure Blob, or GCS. Because compute and storage are completely separate, multiple warehouses can read from the same data simultaneously without interfering with each other. Once computation is done, the results flow back to the cloud services layer, which handles result caching, access control, and finally returns the output to the user. In short, the cloud services layer plans, the compute layer executes, and the storage layer serves the data. That's how these layers talk to each other seamlessly and independently, giving Snowflake its elasticity, concurrence, and high performance. How does Snowflake separate compute from storage, and how does this separation help us? Snowflake separates compute from storage by designing them as independent, loosely coupled layers that communicate only through metadata managed in a cloud services layer. The storage layer sits on cloud object like AWS S3, Azure Blob, or Google Cloud Storage. When data is loaded, Snowflake automatically breaks it into compressed, immutable micropartitions and stores rich metadata about each one, like value ranges and statistics, which enables intelligent pruning later. The compute layer consists of independent virtual warehouses, each with its own CPU, memory, and cache. These clusters don't store data permanently. When a query runs, they fetch only the necessary micropartitions from storage, process them in memory, and then release resources once done. The cloud services layer acts as a coordinator. It knows where each partition lives, manages metadata, and routes queries efficiently between compute and storage. This clean separation allows Snowflake to scale compute and storage independently. And the benefit of this separation is massive. First is elastic scaling. I can add more warehouses for concurrency or pause compute to save cost without affecting the underlying data. True concurrency. Multiple teams can query or transform the same data at once without contention because each warehouse runs independently. Next is cost control. Storage is built at a low, predictable rate, while compute is pay as you go. I can pause or resize warehouses anytime without affecting stored data. The architectural split storage for persistence, compute for processing, and cloud services for coordination is what lets Snowflake deliver cloud scale performance with minimal tuning and maximum cost efficiency. What type of system is Snowflake? OLTP or OLAP? And why? Snowflake is primarily an OLAP system. It's built for analytics. In OLTP systems, like banking or e commerce databases, the focus is lots of tiny, fast transactions, inserting or updating a few rows at a time. Instead, Snowflake is optimized for scanning and aggregating large data sets. Its columnar micropartition storage and massively parallel compute make it ideal for reporting, dashboards, trend analysis, and heavy analytical queries. Snowflake is adding features like hybrid tables for more real time use cases, but its core strength is still OLAP. How does Snowflake ensure data consistency across multiple virtual warehouses, reading and writing to the same tables? Snowflake maintains consistency by managing all metadata and transactions centrally through its cloud services layer. Even though multiple virtual warehouses can read or write to the same tables, all transactional control is coordinated centrally. When I run a query, Snowflake gives it a consistent snapshot of the data. So, readers always see a stable version even if other warehouses are writing at the same time. That's possible because Snowflake storage is immutable. Any data changes creates new micropartitions and the metadata simply points to the latest valid version. So writers don't block readers and readers don't see partial updates. They always get a fully committed version. Behind the scenes, Snowflake uses multi-version concurrency control to manage these snapshots. Each transaction operates on its own version of the data, and its metadata layer ensures that only once a transaction is fully committed, do other sessions see it. That's how Snowflake maintains asset consistency even when multiple warehouses are running parallel workloads by combining immutable storage with centralized metadata and MVCC based versioning. What happens behind the scenes when you suspend and resume a virtual warehouse? When I suspend a virtual warehouse, Snowflake simply shuts down the compute resources tied to it. The data in storage isn't affected because compute and storage are completely separate. Internally, Snowflake deallocates the compute nodes, but it keeps the metadata and cache pointers for a short time. That's why, if I resume the warehouse soon after, it starts almost instantly, often with warm cache. When I resume, Snowflake reprovisions compute nodes and reconnects them through the cloud services layer. If it's been a while, cache may be cold, but query performance still stabilizes quickly. So essentially, suspension is about releasing compute to save cost, and resuming is reactivating compute with the same context. Snowflake handles the entire process automatically. There's no data movement or manual overhead. How does Snowflake handle metadata? Where is it stored? Snowflake stores all metadata centrally in this cloud services layer, not in user storage. The metadata include table structures, statistics, and access privileges. Because it's centralized, every warehouse reads from the same source of truth, which keeps data consistent and query planning fast. It's also cached in memory within the cloud services layer, so query compilation and optimization happen quickly without scanning the actual data. How do the storage and cloud services layers coordinate data and metadata? In Snowflake, the cloud services layer acts like the brain, and the storage layer is the body that holds all the data. When I run a query, The cloud services layer first looks up the metadata. It knows exactly which micropartitions hold the data I need, where they live in cloud storage, and what filters can help skip unnecessary partitions. It then passes this execution plan to the compute layer, which pulls only the required micropartitions from the storage layer based on the metadata. While the query is running, any new data written or updated is also tracked through metadata. New micropartitions are registered in the cloud services layer, while older ones remain available for time travel or cloning. What happens to running queries if a warehouse fails? Well, if a warehouse fails, Snowflake automatically detects it and reroutes the workload to healthy nodes. Since query state and metadata are managed centrally in the cloud services layer, Snowflake can restart the affected queries from the last known save point instead of starting completely over. The data itself is never at risk because it lives in durable cloud storage separate from compute. In most cases, users experience only a brief retry or delay, not an outage. The automatic recovery is part of Snowflake's self healing architecture, where the platform handles node failures transparently without manual intervention or data loss. How does Snowflake handle semi structured data like JSON or Parquet internally, and how does it fit into its columnar architecture? When I load semi structured data into Snowflake, it gets stored in a special column type called variant. But under the hood, Snowflake still maintains its columnar micropartition format. During load, Snowflake automatically parses the JSON or Parquet, extract the keys and values, and builds internal metadata about each field. Things like field names, data types, and value ranges, all stored in compressed columnar form. So, even though the data looks flexible in structure, Snowflake can still apply pruning and column level compression just like structured tables. When I query it using dot or colon notation, Snowflake doesn't parse the entire JSON blob. It leverages that internal metadata to retrieve only the relevant fields. That's why semi structured queries in Snowflake perform so well without pre flattening. In short, Snowflake treats JSON like structured data. It just pushes structured discovery and optimization to the storage layer, which keeps queries both flexible and fast. And that wraps up episode 1, Core Architecture. These are the questions that test how well you understand the engine under the hood, not just how to use Snowflake, but how it actually works. Up next, we'll move from architecture to data lifecycle and recovery scenarios, where we talk about time travel, failsafe, and how to design tables for both cost and durability.